2 shows the relative energies of reactants and products at certain temperatures. So we got figure 2 number here, and as the reaction progresses, this is the reactants, they have this much energy, the reaction happens, and then you got the products with this much energy over here, and this would be the energy in kilojoules. Okay, now normally when you do these energy level diagrams in class, you wouldn't have numbers here on the side. You would just expect to know that obviously that is higher than this one, therefore this one will have more energy than this one over here at the bottom. Okay, now the question is, label the activation energy on figure 2. This is only 1 mark. Now this is very important. You need to make sure that this is a dotted line. Okay, and the activation energy will go all the way to the tip. That's a bit wonky, isn't it? There we have it. There we go. So that is what you need, and that's going to be your activation energy. But remember, you need to label it. So we're going to write there activation energy. And that is your very first mark on question number 3. Let's go to questions 3.2. Okay, determine the overall energy change from each reaction between hydrogen and oxygen in question 3.1. Use figure 2. Right, so we're gonna have to go back. We're gonna try to calculate the overall energy change. Now, if we look at here and we trace this, that's gonna be 500, 600, 7, 8, 9, 10. So that there, we're looking at 6, 7, 8. That's gonna be 800 joules of energy, 800 kilojoules of energy. And the product, if we trace it along, normally you do this with a ruler, but I believe my eye is good enough for this. So we have 100, 200, 300, okay, joules of energy. You are always going to take away the energy from the products out from the energy of the reactants. Okay, so we go back to the previous page. We're gonna go energy in, take away energy out, and that is your answer right there, 500 kilojoules. And that is a very, very easy 2 marks. Okay, so let's go to question 3.3. Now in here it says oxygen is in group 6 of the periodic table. Figure 3 shows the outer energy levels of one molecule of oxygen, O2, that's O2, so there's 2 oxygens in there. Draw the electrons in the outer shell and the outer energy levels in figure 3. So your clue in this question is right here. That is telling you the oxygen is in group 6. Now, this is called a dot and cross diagram, so you should make the dots as the electrons of one of the oxygen and X's or crosses as the electrons of the other oxygen. Now, remember that the atoms need to have 8 electrons in an outer shell in order to become stable, but every single one of those 2 oxygens has only got 6 electrons in the outer shell, and that's why they are in group 6. So they are going to be sharing 2 electrons each with each other. Okay, so if this oxygen has the excess, that's going to be 1 electron, 2 electrons being shared, and it has a total of 4 electrons. A total of 6 electrons. So that's 1, 2, 3, 4, 5, and 6. There you have it. So the same is going to be on the other side, but this time we're going to do the circles. 1, 2, 3, 4, 5, and 6. Now, this is going to have 8 electrons, including the ones that is borrowing from the other oxygen, and so will this one, and that is your dot and cross diagram completed. That is 2 marks. You're going to get 1 mark for having this section in the middle correct, and you're going to get the other 1 mark, for having the outside of both molecules correctly drawn as well. Let's go to question 3.4. Okay, in this question, we're looking at calculating bond energies, okay? 3.4, this equation shows the decomposition of hydrogen peroxide. So you have 2 molecules of this, and that breaks down into 2 molecules of this and 1 molecule of that, okay? Right, so let's have a look at what we got here. calculate the overall energy change in the reaction. Now I'm gonna do this a little bit in the long way just to make sure that you understand what we're doing, and then once you get used to it, once you master the technique, then you can shorten it up in whichever way you want to do it. But let's go with the basics. We're gonna calculate the overall energy change, so we gotta calculate the difference in energy going in and energy going out. So we're gonna start calculating the energy going in. Right, so over here is your difference. Before the arrow, that's the reactants. After the arrow, that's the product. So we need to calculate how much energy is going to be needed to break those down, because the reactants need to be broken down before they can be turned into products. So we have OH bonds. So we have an OH bond over here. There we go. That's one. And we have an OH bond over here, and that is two of them. So OH bond is 463. So when we look at OH, we're looking at 463, and that is two of them. So we're gonna do times 2. Then we also have an O single bond O single bond O, and that is going to be O single bond O, and that has a value of 138. There is only one of them there so far, so we don't have to multiply by anything. So let's do this one over here, and if you mental math are good, then that's okay. Mine was a good, but I just want to make sure that this is correct. Don't be afraid of using your calculator, okay? So let's see. So we got 463 times 2, and that's going to give us 926. So we're going to go for 926 plus the 138 from here, plus 138 equals 1064, but this is just for the one molecule. This is telling me that you have two sets of those molecules, so we're gonna times this whole thing by 2, and that's gonna give me 2128 kilojoules per mole. Now in the other side, we're gonna do the same thing. We have an OH, and then we have another OH over here, so we're gonna go OH, OH arrow, that's gonna be 463, and that will be times 2, and that's gonna give me also 926. Now I also have to multiply this whole thing by 2, so I'm gonna do that times 2, and that's gonna give me 1852. Now I'm gonna do the same thing for the oxygen over here. So oxygen double bond O is gonna be 496, and I've only got one set of those. That 2 doesn't apply to that because it's before the symbol, so that is just that. And I'm gonna do 496. I'm gonna add those two together, plus 496. That's gonna give me 2348. Okay, now the only thing I have to do is take away the product's energy away from the reactant's energy. So I'm going to do 2128, take away 2348. That gives me 220 minus 220. That is your answer right there. And because it's a negative number, we can tell that this reaction is an exothermic reaction, meaning that energy was lost to the surroundings. And that's it. That is question 3 completed. So click on the next video so we can look at question number 4. Right, so there you have it. Quick time revision. Like and subscribe, and I'll see you next time.